Hello, this is recording for homework 8. In problem 1, we have a wheel rotating about the axis. This is pretty much rotational kinematics. The quantities we look for always are 5 variables like in the linear kinematics. The time remains the same. Instead of linear displacement, we have angular displacement, which is given to us to be 80 radians. So it's one significant digit actually in that. Time is 4 seconds. We have omega initial angular velocity, final angular velocity. Neither one of them is given to us, and the angular acceleration is 4.0 radians per second square. In the part A of the problem, we are interested in the initial angular speed. That means we have to look for an equation that has the final angular speed as a missing quantity, and that is delta theta is equal to omega initial delta t plus half alpha delta t squared. Putting in the numbers, we have at is equal to omega initial times 4.0 plus, and delta t is again 4.0 square. That gives us the value for omega initial. This number here is 16 into 32. 80 minus 32 is 48 divided by 4. That's 12 radians per second. So omega initial is 12 radians per second. Since 80 has only one significant figure, you can also say this is 10 radians per second. Part B, we try to calculate omega final. It's exactly similar equation, which does not have omega initial this time. It's the final delta t minus half delta t squared. That's all the difference. Most of the things remain the same. It's 4.0 except for the sign, which is and again, this quantity remains the same, 16 into 232, but this time we add to 80 instead of subtracting, so that's 112 divided by 4. So its final velocity is 112 divided by 4 would be 28 radians per second. And again, uh, since we want to keep one significant digit, because 80 has only one significant digit, this will be 30 radians per second. And let me pause for a minute. In problem 2 of homework 8, we have a turntable on which we keep a penny, and the turntable is moving with a constant angular speed. So let's say we take a circle that I can draw. So I think that's your circle, and that's the center, and that's the penny. If I were to look at this this turntable from a cross-sectional point of view. This is the center of the turntable, and we have the penny, which is being shown as a box in this case. That's your penny, and the forces acting are mg that acts downward, the normal force acts upward, and the tendency of the penny is to move outward as this rotates. So if this is your rotational motion, so that's omega, and in this case it is going into the whiteboard, and this could be a radius r, the distance from the center where the penny is kept, and that distance here in this diagram is r. Since the tendency of the motion for the penny is to move outward, the force of friction is inward. Writing down our, so let me go by definition. So part A, let's ask us to identify the forces. So it's of course mg, the normal force, and the force of friction, which means our Newton's law will be stated as ma is equal to mg plus the normal force plus the force of friction. We look for, we break this equation into the radial and vertical direction. So in the radial or horizontal, let's say horizontal direction, we have mass times acceleration. In this case is, so acceleration is omega square r, where omega is the angular speed with which the turntable is rotating. So that's m omega square r, and that's provided by the force of friction. In the vertical direction, we have no acceleration, and we have minus mg plus the normal force. This should be, like I've used some shortcut here, and in the horizontal direction there is no component for the mg, there is no component for the normal force, it's only the force of friction that survives. And it's the opposite for the vertical direction, there is mg and normal force as components, but force of friction has no component in there. And since the mass does not accelerate in the vertical direction, we have acceleration due to gravity, or acceleration to be uh, 0 in this case. Force of friction also has to be less than or equal to mu s times the normal force. So let me first answer the question in part B. It's clear from here that the force, what provides the centripetal acceleration, it is the force of friction. So force of friction provides the centripetal acceleration. What is the farthest distance away from the axis of rotation of the turntable that you can place a penny so that the penny does not move or does not slide away? That's given by the inequality in here, when the force of friction barely is at the threshold. And we are also given mu s. So for part C, we have to equate m omega square r, that's your centripetal force, centripetal acceleration times the mass. It's to be less than or equal to mu s times n, but n is equal to mg. In the vertical direction, we have n is equal to mg. Substitute that in here, there's mg. But the mass cancels out, and we are interested in how far can we go. So that means r has to be less than or equal to mu s times g over omega square. And we can put in the numbers, one significant in the coefficient of static friction, so it's 9.8, and omega is given to be 6.5 square. This can be calculated, and we need to keep only one significant digit. 6.5 square. So that's 0.12, so that's 0.10, 0.1 meters. That's 10 centimeters. But there's only one significant digit in this. Let me pause again before I start the next. This is homework 8, problem 3. This discusses an angular motion, a rotational motion of a fan blade. We are given the angular acceleration for the fan blade, which is alpha, to be 10 radians per second square. The three significant is that at what point on the blade, as measured from the axis of rotation, does the magnitude of the potential action equal to that of the acceleration due to gravity? We call tangential acceleration, which is not the radial. Radial is the centripetal acceleration. It's angular acceleration times the radius for r, and we are asked to find out when does this equal 9.8. So tangential acceleration is 9.8. So at what radius? So this is given to be 9.8 meters per second square. So acceleration due to gravity. Alpha is 10.0 radians per second square. And at what radius r does that happen? So r will be equal to 9.8 over 10.0. So that's 0.98 meters. Right? And we can keep two significant digits because 9.8 has only two significant digits. That's all there is to it. It's reasonably straightforward. Pause again. In problem 4 of homework 8, we have a rotational motion of a tire of a motorcycle that is accelerating linearly at acceleration is not given, but we are given quantities for the linear motion, and we should remember that the linear motion gets connected with angular motion through the radius. So we have delta x not given to us. Delta t is 8 seconds with 3 significant digits. V initial, it starts from rest, so that's 0. V final is 24 meters per second. And acceleration is not given to us. So we have 3 quantities. We are interested in the angular acceleration. That means if we can find the linear acceleration, that will be equal to it will be connected with the angular acceleration through the radius r. So the missing variable will be delta x. So the quantity is, we say acceleration is v final minus v initial divided by delta t. V final is 24 minus 0 divided by 8.00, so that's 3.00 meters per second square with 3 significant digits. Once we have the linear acceleration, Angular acceleration and linear acceleration is related by a is equal to alpha times r, where r is given to us to be 0.300 meters, right? So it's about 30 centimeters, again given to three significant digits, so we can calculate alpha, a over r, that's 3.00 divided by 0.300. So that's 10.0 radians per second square. And that will be the magnitude of the angular acceleration of each of the guys. So that ends the recording.